Resonance between parallel RL and RC circuits. At R1C in one branch, R2L another branch, both are in parallel and they are parallel with the voltage V having the variable frequency F. Now let Y1 admittance of R1 and C and Y2 is the admittance between R2 and L, and Y is the total admittance which is given by Y1 plus Y2. The current flowing through the capacitor IC is given by V by Z RC, and IL is the current flowing through the RL branch, that is V by Z of RL. Then Y equals to by R1 minus J XC plus 1 by R2 plus J XL. Total admittance is given by multiplying this with 1 by R1 minus J XC with R1 plus J XC divided by R1 plus J XC plus here 1 by R2 plus J XL, multiplying this with R2 minus J XL divided by R2 minus J XL. Then we'll be getting R1 plus J XC divided by R1 square plus XC square plus R2 minus J XL divided by R2 square plus XL square. Separating real and imaginary terms, we are going to get R1 by R1 square plus C square plus R2 by R2 square plus XL square is real term plus J of XC divided by R1 square plus XC square minus XL divided by R2 square plus XL square. And the circuit will be in resonance when the imaginary parts of capacitive and inductive admittances are cancelled. At resonance, XC by R1 square plus XC square is equals to XL by R2 square plus XL square. XC of R2 square plus XL square equals to XL of R1 square plus XC square. Now substituting the values of XC, 1 by omega naught C of R2 square plus omega naught square L square equals to omega naught L of R1 square plus 1 by omega naught square C square. If R1 square equals to R2 square equals to L by C, and this equation is going to be modified as L by omega naught C square plus omega naught L square by C, which equals to omega naught L square by C plus L by omega naught C square, which is nothing but RHS equals to LHS, provided R1 square equals to R2 square equals to L by C, or provided R1 equals to R2 equals to square root of L by C. The circuit will be in resonance for any frequency provided R1 equals to R2 equals to L by C. Now, again in the same circuit, IC sin phi 1 equals to IL sin phi 2. We know the IC and IL. Now sin phi 1 equals to XC divided by ZRC, and sin phi 2 equals to XL divided by ZRL. Now substitute this V by ZRC, XC by ZRC equals to V by ZRL, XL by ZRL. 1 by omega naught C multiplied by ZRC whole square, that equals to omega naught L divided by ZRL whole square. Now substituting these values, 1 by omega naught C of R1 square plus 1 by omega naught square C square, which equals to omega naught L divided by R2 square plus omega naught square L square. Omega naught C by R1 square omega naught square C square plus 1 equals to omega naught L by R2 square omega naught square L square. R2 square plus omega naught square L square equals to L by C of R1 square omega naught square C square plus 1. R1 square omega naught square L C plus L by C. Omega naught square L square minus R1 square LC is equals to L by C minus R2 square. Omega naught square equals to L by C minus R2 square divided by L square minus R1 square LC. After simplification, 1 by square root of LC, L by C minus R2 square divided by L by C minus R1 square under the square root, which is nothing but omega naught. Now the resonance frequency F naught is given by 1 by 2 pi root LC of L by C minus R2 square divided by L by C minus R1 square. This is our resonant frequency for parallel RL and RC circuit.